You are not in grade 10. You sit down. Okay. Actually, if we're going to be really honest, Sienna, you know what? Never mind. I would never say that to you. I was going to say, you present older, but you look exactly the same as the little girl who sat over there in my grade 9 class. Block D. Math 9, I can still see you. You talk older, but I can still picture you over there. You haven't lost your enthusiasm, which is a very positive thing. You're in grade 10?
Yeah.
Nice. I was not expecting that. Have fun. Okay, find me this page if you haven't already. Here's the answers. Boom. Are there any comments, questions, concerns? Is there anyone who would like me to demonstrate any of the things? I wanted you to do these with the factor label method. I didn't give you a lot of space, so you needed to do this on your own space. Either lined paper or on the boards or on the whiteboards or... I wanted you to practice the method. Is there anything anyone would like me to demonstrate? Compare your answers with my answers. For the questions involving the year, I did in fact use the accurate number of days that are in a year. The reason we have a leap year every 4 years is because a year is not 365 days long. It's 365 and a quarter days long. And so you have to actually take that into account when you're dealing with question 3 down here. My answers take into account that extra quarter day. Which, I mean, a quarter day is only 6 hours, so it doesn't change your answer that much. But comments, questions, concerns? Once, twice, thrice. Sold. Okay, cool. I also wanted you to take a look at this page here. I gave you the answers to this one, though, so you were able to check it ahead of time. The answer key for this page is right here. Is there anything there anyone wants me to demonstrate? Any of these conversions that anyone would like me to show them? Going once. Twice, thrice, sold. So that means everyone either did them perfectly or didn't do them at all. I like the first one better. Okay. Hearing nothing. Flip ahead, find me this page. We're going to have a conversation about scientific notation. Now, there's actually more going on this page that I'm actually going to get you guys to do, but I do want you to be at least aware of the power of scientific notation, and lots of you are. Some of you did in the middle school. If you had, those of you who had me for pre-diploma math 9, I do it there. But that might be the only place. Like if you didn't see it in pre-diploma 9, if you didn't see it in grade 8, there's a real possibility that you haven't seen scientific notation anywhere else. And so we're going to review it here a little bit. Scientific notation, what's it used for? Why is it a thing?
To make if there's a goal which is 0, to make it more compact.
So
It turns
simplify what you just said.
big number with a whole bunch of zeros turns into a small number times 10.
Okay.
The exponent of however many zeros there were.
Makes big numbers smaller or more condensed. Yes, and we do this by tweaking them, by moving the decimal around and then making them times 10 to some power. So I've got 2 examples here. Does anyone recognize either of those numbers? 299,792,458. What is that number? That is the speed of light.
Some sort of molecule.
Speed of light. So then the units on this are in meters per second. 299,790,458 meters per second is the speed of a single photon of light, which is ridiculous. This is the universal speed limit. Nothing goes faster than it. You will never see it written like this. This will often get condensed. Scientific notation, though, condenses this by taking the decimal where it is, so here at the end, and moving it. So we're going to move the decimal point until only one leading digit, and that leading digit has to be non-zero. We want that leading non-zero digit is the only thing we want to the left of the decimal place. So what we're going to do is we're going to take the decimal that's at the end there, it's implied, and we're going to move it 1, 2, 3, 4, 5, 6, 7, 8 times. So it's going to become 2.9979245.8. But obviously 2.99 is not the same as 299 million. So we rewrite, well, we don't rewrite it, we add something to it. We go times 10 to the power of what? How many times did we move the decimal? We moved it 8 times. And so we put the times 10 in there, and we put the exponent, in this case 8, the number of times we moved the decimal. You want to have this exponent be such that if I actually multiplied this thing back out, it would put the decimal back where it belongs. So this times 10 to the 8 is very, very large. 10 to the 8 is 100 million. But this looks like more work because we actually had to add 1, 2, 3, 4 more things. So in this case, we wouldn't actually write it like this either. With scientific notation, what do we often do? What do we always do? Five letters, starts with an R. Yes, Thor. You round. So we don't write 299,792,458. We round that to 3 times 10 to the 8. And now you actually have something condensed. What's another, what is it, 208,000 meters per second? When you're already moving 299 million meters per second, what's another 200,000, right? Effectively, the speed of light is 3 times 10 to the 8 meters per second. That number is already incomprehensibly large, that we have no problem rounding it and then using that value as the speed of light. The number of spaces that we moved is, as we said already, the exponent. To put the exponent where it was, we moved left. And so when we move left, the exponent is positive. Because when that exponent is positive, the number is really, really big. 10 to the 8 is a massive number. So here's a second number. In this case, that number is, that's a lot of zeros. After the decimal, there are 33 zeros. I did the counting already for you, so you don't have to, unless you've done it already. Does anyone recognize that number? Yes, Andrew.
I'm guessing it's like the weight of a neutron or electron or proton or something like that.
Reasonable guess, but no. Smaller than that, actually. Oh, this number is smaller than that weight. Okay, this is a number called Planck's constant, which is not something that we use in Physics 11. I just wanted to pick a ridiculously small number for effect, because, you know, why not talk about these? This number, there's 33 zeros, which means that there's 33 jumps to right there. From right there to right there is 33 jumps. But for scientific notation, we want to move the decimal point until only one leading digit remains. The digit isn't leading unless it's out front. So we've moved it 33 times to get past all the zeros, and then we got to go one more time to get to that first 6. So we've actually moved the decimal place how many times? 34, thank you. So there are 34 jumps. You don't have to count it. I did it already for you. So then we're going to rewrite this number as 6.626 is usually how you'll see it, times 10 to the what? This number is very, very small. And so to denote a very, very small number, or one way to denote a very, very small number, or like a decimal number like this, is to write it as a fraction. And if you have an exponent in a fraction, then the exponent has to be, louder, negative. So here we want the exponent on the 10 to be negative to denote that this number is very, very small. So this is going to be 6.626 times 10 to the negative 34. It's Planck's constant. Very tiny value. When you move the thing to the right, the exponent is going to become negative. And so obviously when we undo these things, if the exponent is negative, we want the number to be small. And so if I wanted to go back and write it like this, a small number means it's got a bunch of zeros in front and then a decimal. So we just crank it back the other way, this many times. If you want the number to be large, obviously the decimal is not written. So it's after the leading digit. It's going to go back the other way. Yes, Andrew.
So what is actually Planck's constant?
What is actually, Planck actually has a few constants, and I don't remember which one I put down. So let me read it for you. Planck's constant. Planck's constant is a photon's energy multiplied by its frequency. So there are constants that we deal with all the time. There is something called the universal gravitational constant, which I will show you when we actually get to it. It is... Did you guys talk about gravity last year in Science 10? What is the value you used for the acceleration due to gravity? 9.8. So that is not a constant. That is true on or near the surface of Earth. To calculate it, to truly calculate that value 9.8, you have to use a formula that you weren't shown in grade 10 that I'm going to show you this year. The formula involves the mass of the object creating the gravity, Earth, the radius of Earth, and then you need a multiplier out there called the universal gravitational constant. I'll show you what that now. I'll tell you what that number is in a couple chapters. Just like that, to find the energy of a photon, you take the frequency of the photon, which is related to the wavelength of that photon and the speed of light, because all light moves at the same speed, but there's different frequencies and wavelengths that photons have. To figure out how much energy is there, you take that value for the frequency and multiply it by that number. And that will give you, that is the universal constant to find the energy of a photon. Again, not something that we use in Physics 11 or even in Physics 12, but if you go off to special relativity or particle physics, this is a value you will need. It has units. The units are joules per hertz. Both of those values will make sense in later chapters, or units will make sense later in those chapters, but that's what that value is. I just wanted to pick a really, really small number to justify the use of scientific notation. Now, if you're not comfortable with scientific notation, I will never require that you put your answers into scientific notation. If you don't want to use it, you don't really have to use it, but scientific notation is a really powerful tool. We use it in physics all the time for a few different reasons, one of which I'll show you possibly today, but definitely tomorrow if not. And it is often how I will give you your answers to the homework that I give you. So you might have done all of your work with normal values and you'll have, I don't know, maybe one of your answers is 2,950 meters. That could be your answer. 2,950. I might tell you the answer to the question is 3 times 10 to the 3 meters. And so what you need to do is you need to recognize that 3 times 10 to the 3 is 3,000, and your answer, 2,950, rounds to 3,000, and therefore your work is correct. You don't need to do math and scientific notation, but you need to be able to convert into and out of it. This is why we do it here. So I'll do 2 of these, and then I want you to crank out the rest of these. If we're going to write the following numbers in scientific notation, what would I do with that? If there is no decimal written, where's the decimal always? What is the words for that? Hand gesture. All the way to the right. If there isn't one, there it is. Don't be like my grade 9s who were assuming that all those commas were decimal places, which would be confusing and not mean anything. That happened this morning. The decimal, if there's not one written, is all the way there at the right. And so we're going to move it over. 3, 6, 9. You have to have one digit in front. There's going to be one non-zero leading digit. So it's going to be 5.5 times 10 to the however many times we jumped. We jumped 9 times. We jumped to the left, so that number is going to be positive. 5.5 times 10 to the 9. The only difference with the small ones is that the exponent's going to be negative, so I'm not going to do those. I'll let you do those in a second. If I wanted to go the other way, you have to recognize what these negative and positive exponents mean. If the exponent is given to you negative, it means the number is going to be less than 1. It's a small number. So if I have 5.5 times 10 to the negative 4, how you'll write that out is this. The less you can do in your head, the better. Show me the work. So we're going to start with the 5.5. I'll write out my 5.5. The decimal's there in the middle. If the exponent is negative, which way do I have to go to undo scientific notation? If I go to the right, that means the number is going to be really big. The negative exponent means I want the number to be small. And so I have to go back left. So we're going to go 1, 2, 3, 4. And all of these spaces, 1, 2, 3, get zeros. So then 5.5 times 10 to the negative 4 is going to be 0.00055. I want you to crank out those other 5 real quick, and I'll walk around and give any clarifying questions. This is just a crash course review of scientific notation, which you would have seen in those. Yes. You have questions? Let me know. Oh, did you forget your booklet, or do you not have a booklet? So I have extras for it. If you would like, I can give you a copy of the booklet. You write down all the pages that want, tear them out, and take them home and just insert them into your book. For that, or do you want to do what you want? That works good. Okay, that's fine. So you're going into and out of scientific notation. Even scientific notation. 10 to the 3 times 10 to the 5 is not. Oh, with the thing across. Okay. So yeah, I mean 10 to the 8 is sufficient. We're not actually because it's not pointless. But I'm not going to make you do scientific notation. So I'm actually going to skip that one. It is just an exercise. It's all an exponent loss.
But if it's so big that all those years don't count.
Yeah. That's loss.
They were simply.
Go for it. Do the work then.
Yeah. We have no.
No calculators. No calculators. They're just testing. That's correct. Twice as small.
Wait, what if we do some more of the great graphic skill?
Yes, I suppose you can do that. This one. Okay, some of you have already flipped the page and started working again. So once you are done these 5, we're going to skip the compute the following. I used to have it in there because I actually used to get you guys to do work with scientific notation, and I'm not going to bother with that now. Once you're done those 5, I want you to flip the page. And there is a chart there that says estimate an object. And I give you a bunch of scientific notation sized scales. There's a 10 to the negative 9, 10 to the negative 6, negative 3, negative 2, 0, 10 to the 3, 10 to the 6, and 10 to the 9. What I'd like you to do is, after you've done this 5, flip to that page and brainstorm with your table objects you think would reasonably be on, that we would reasonably measure, I'll say it that way, reasonably measure with that scale. So for example, 10 to the 0, anything to the power of 0 is 1. So if you had 10 to the 0 meters, that means that that object is 1 meter long. What is an object that you would measure easily with a meter stick? Not, yes, use a meter stick to measure meter sticks. What is another object that you could reasonably measure with a meter stick? Sorry? A human, a person. Absolutely. We are on the scale of 10 to the 0. So 10 to the 3 would be 10 to the 3, 3 zeros, would be 1,000. What are the kinds of things that you would measure on the thousands of meters? So the kilometer scale. 10 to the 3 meters is a kilometer. So what kind of objects would you measure? And so I want you to go through, there's 7 of them there? Yeah. I said it again, I'll say it again, -9, -6, -3, oh, no, more than that. -2, 0, 3, 6, and 9. Just don't look anything up. Discuss with your table objects that you would measure on those different scales. And in a couple minutes, we'll actually show you a whole ton of objects that would satisfy that. Finish the scientific notation stuff and then jump there. Just to give you perspective on some of these numbers. Don't fill in the right-hand column. The right-hand column is actual objects. Let me give you examples of real objects. Stay in the left-hand column. Well, a football field's how many meters long?
I know it's 50 yards.
It's not 50 yards long, it's 100 yards long. And a yard and a meter are almost the same. A yard is 3 feet and a meter is 3.2 feet. So, for all intents and purposes, basically the same. So you can say it's just over 100 meters. Or it's just under 100 meters.
How am I going to measure anything that's a gigameter?
But think about it. Okay, so like what is a gigameter?
Like,
A gigameter is giga the 10 to the 9. So there's 9 zeros. So that would be this transition out of meters into kilometers maybe. So kilometers means I'm just hacking off 3 zeros. So now you're on, instead of the billion meters, no, is it billion meters?
I think more than.
Hold on, where are we here? 9 zeros. 9 zeros, that's a billion. You're taking out the last 3 zeros. And so you're looking at a million. What is something that is measurable on the scale of millions of kilometers? Evening. You said country, you said universe. Somewhere between those two is going to be the satisfactory answer. Like, I'm just, all I'm doing, don't look anything up, just guess, what are you able to picture based on your understanding of scale?
For nanometers, are you thinking cells or
Just making guesses.
Atoms.
Yeah, that's your guess. Make the guess.
Atoms. Are going to be quantities.
I mean, there's ways to think this through, right? Like, so if the centimeter, do you really? Because the small thing is this is about a centimeter. So then a millimeter is 1/10 of that.
A centimeter. Or a centimeter.
A micrometer is 1,000 of that down. So there's 1,000 things in between my fingers. Like we're talking about micrometers. How thick is your hair? You had 1,000 hairs? Or is it maybe smaller than it? You have one hair hanging out right here. You can easily see the width of one hair as it hangs. You want to just look at the words inside. You can obviously see the thickness of the hair. Yes, you're just making a guess. I will show you in a second. Make some guesses.
It's somewhere between.
Yeah, Earth is between.
Mine's down. It means the denominator is very small. This number is and so when you make it 5.5, this that multiply by also that needs to be a positive. So if you don't want it to be multiply this by 100.
Well, I actually not.
Yes. Yes. I know it's really hard to do. So I want you to pick an object that you think you might be wrong. That's fine. What kind of objects would you measure on some of these things? Centimeters is easy, right? What kind of objects would you measure that are like this? I can see several objects, but this would be useful. You measure in centimeters. Ample probably be but even that, like, a meter is this, centimeter is this. Anything smaller than this is useful to measure in centimeters. So, thickness of a pen. Embrace, like, there's all sorts of things around you that would make sense to measure in centimeters. That's all I'm asking. What kinds of objects do you measure in centimeters? What kinds of objects do you measure in millimeters? Make up pictures of what you think might be true. Make a guess. What are objects? Obviously, this is very small. So, what do you think of that as very small? What do you think might be that small? I can't think of anything small. Single strand hair, but I can see the single strand hair. Can you see bacteria? No. So I can see the bacteria, but I can't see the hair. That means hair is not hair may be different, but it's definitely not because it's smaller than the bacteria. This is small. What's the cell? Blood cell. Maybe. I'm going to show you in a second a sliding scale of the universe. You'll see what kinds of objects. All I'm asking you to make is a reasonable guess based on the things that you're familiar with. We'll find out.
That's like a really birthday present.
In a couple minutes, I'll show you the scale.
In one time.
Because you don't want to be wrong. It is. Absolutely it is. Okay, some of you are scared to guess, and that's okay. You're just walking around and seeing I can appreciate the difficulty. You're scared of getting it wrong, and so you don't want to start. This is easily the most painless thing I could possibly give you. I just want you to make some estimates, and if you're wrong, who cares? I'm not going to mark you on this. Those of you who are scared to even guess here,
I would like you to think about that and think about why and mull how you're going to get over that. Because if this was a difficult exercise for you and just even being willing to toss out a guess, I very much identify this. But we are the kind of people who, if you're stuck, I'm going to suggest, perhaps you tell me if this is wrong, but if you don't know where to start, you're scared to try. Don't have to answer that. But if that's you, the sooner that you can get over that, especially in this course, the better off you will be. And that's why I'm going to encourage you to use the whiteboards. That's why I'm going to encourage you to use, even pencil. The less permanent, like there was no, what's the word I'm looking for? No danger in this. And yet there was a ton of us who were scared to even write anything down for fear of being wrong. You're going to be wrong, and that's okay. Just my little pep talk for that. Okay, before we do that, I want to give you answers to these just to make sure we're all on the right page here. I'm going to go back and give these answers in, why not, hot pink, because hot pink is awesome. Here we go. This should be 9.1 times 10 to the negative 2. 7.8 times 10 to the positive 2. 3.004 times 10 to the negative 6. This is going to be 7,100,000. So 7-1 followed by 5 zeros. And then this number here is going to be 1,000. So all it is, and I'm not going to expect you to do this a lot, but actually, I'm not going to expect you to do this part at all. But this you need to be able to do comfortably, because a lot of the values that I'm going to give you for the answers to the stuff I'm going to give you is going to be in scientific notation, and you need to be comfortable enough to either put yours into or pull the answers out of and work back and forth between those. So, were there any questions about these 5? Is there anything anyone wants me to explain? Okay. I'm not going to do this. We are going to skip this part. I am not going to require that you operate in scientific notation. If you want to see it, I can show you. If you've done, I know, Andrew, you want to see the answers. Okay, come see. I've got the answers right here. I'll show you later. But I am not going to do it now. We're going to do this. First, I would like to hear some of your values, and then I'm going to show you objects that are on this scale using a fun little website. So, let's start in the middle. You guys said as a class that an object that you could reasonably measure on the meter scale, so objects that you would measure with a meter stick comfortably, is a person. Not all people. I wouldn't measure every person with a meter stick. My son Jack is pretty short. My daughter is basically the perfect example. She's almost exactly a meter tall right now. Jack's pretty short. But any normal person over, 4-year-old's height measuring with a meter stick would be totally reasonable. Or are there any other objects any of you said would be conceivable around the meter scale? A meter stick. Same thing they said over there. I don't know if it was Thor or Andrew. Someone said it over there. What other objects? Not the measuring device itself. Did no one say anything other than a person? Yeah. A flag. That thing. Absolutely. Why not? Some flags, you bet. The ones that are hanging in my room. Actually, even the ones hanging outside. How about objects on the... Should we go big or small first? Let's go small. The centimeter scale. What kind of objects would you reasonably measure as a centimeter? And a centimeter is like yay big. You guys have all seen a ruler before? Yes. A pea. P-E-A, not P-E-E. You betcha. P-E-E, we measure in milliliters or liters. A pea. Okay, cool. What else?
Size.
Sorry?
Screen size.
Screen size.
Yeah.
Like a laptop or a
Laptop, phone.
iPad, phone, okay? Phone, laptop, screen. You wouldn't do that as a TV because, especially that one there, it's over a meter across. You'd use meters. What else? Is it inappropriate? Is that why we're smiling and blushing? Okay. Then what is it? A centipede. Most insects. Yes, you betcha. Insects are generally going to be on the millimeter scale. Not all, but most. There is some insect. My kids love bugs, and they have like The largest bug is the Chinese stick bug, 2 feet long. So you might use centimeters for that, but you might use a meter stick to measure that. There's an insect called the fairy fly, where 300 of them would fit on the tip of my pencil, apparently. You would not use centimeters for that. You would use what? Perhaps millimeters. Maybe even micrometers for a bug that small. Maybe, we'll see. What other kind of objects did you say were on the millimeter scale now?
Millipede.
No, that is incorrect, because a millipede would be on the centimeter scale. You're hilarious. What else? What would you measure on the millimeter scale? Yes, Abdu. Grains of salt?
Oh, yeah.
Grains of salt, perhaps. Okay. What else?
Grains of sand.
Grains of things. Okay. Rice. Grains of rice.
Tool diameter.
Grains.
So like nozzle diameter or whatever you use
Ooh.
to be very precise.
Precision tools. Do any of you have mechanical pencils? What are those measured in? The thickness of the lead. Yeah, there's 0.7. 0.7 means that lead is 0.7 millimeters thick. So here's a really good example. I have no lead. Huh? Awkward. What if I use this pencil? Yeah, this one's got lead. This, just so we're clear, that thickness right there looks really thick on the screen. That's 0.7 millimeters. That's what that number means on the size of, on the pen. See, it says right there. 0.77 millimeter. So you have objects around you that are on these scales. And it's not actually lead, it's graphite, but we'll call it lead. Pencil lead. It's on that scale. Okay, sorry? Because it used to be lead. Now they use graphite, because graphite's not poisonous. Lead is poisonous. Sorry? Yes. Lead paint, yes. Micrometer. Okay, so now we're into the realm of like actually guessing here. Yes. Micrometers. Micrometers, you betcha, sir. Steven.
A pixel on the screen.
A screen pixel. Ooh, let's look that one up. I'm curious now. Yes. Hair. It's interesting thought. Size of screen pixel. Interesting. Oh, there is no defined. Oh, now cool. Interesting. Now you're suggesting a cell. Like skin cells, hair cells, like the individual building block piece. Okay, these screen pixel hair cells, fundamentally very, very different. So now we're into the realm of not everyone can be possibly right here. Yes, Abdu.
What are the wavelengths for light?
Oh boy.
What are the colors?
Now you're talking about wavelengths of light. You saying colored light?
Yeah, what are the colors?
Okay.
Which one?
How do I spell color? O-U-R. Colored light. Okay. We have objects on wildly different scales here. Fascinating. I love it. We'll talk about all of those in a sec. Let's keep guessing. Nanometer scale. What kind of objects are on the nanometer scale? We're talking about atoms? Okay. Perhaps. Did anyone say anything other than atoms? Yes. Okay, so those are proteins are made of atoms, so the protein's going to be bigger. Okay, that's a good guess. I don't know. Let's find out. Proteins. So either chains of atoms or the individual atoms themselves. Sorry? A chromosome. It's good that you picked the Y chromosome because the Y chromosome is actually the smallest, most pathetic of all of the chromosomes. Represent, gentlemen. Smallest and most pathetic chromosome is yours. Yes, Andrew.
Hasn't it shown that the Y chromosome in men has been slowly getting smaller over time or something like that? I read that.
Unrelated, but yes, that is true.
It gets smaller the longer you live because Yes, remade him.
No, generation on generation.
Oh,
The male Y chromosome is shrinking. It means that there's a reasonable it's people have speculated that as a result of this, eventually the Y chromosome will no longer be a thing, which would be wildly problematic for obvious reasons. Nope, I'm going to pull you back, bring you back, because well, part of the reason I'm going to say it anyway. Part of the reason it would be a problem is because then people would have an odd number of chromosomes. You have an odd number of chromosomes, now you can't reproduce. The reason that mules cannot breed, you cannot breed a mule because a mule is a cross between a horse and a donkey, and they don't have the same number of chromosomes. They both have an even number of chromosomes, so you can breed them together, but their offspring has an odd number of chromosomes. So it cannot breed amongst itself. So if the Y chromosome actually disappears, the human race, as we know it, is over.
So what happens?
Some of you would be like, yeah, no more dudes. But you'd also be like, this is the last generation of life on the planet. Everyone dies. It'd be bad.
What happens if you do try breeding mules?
Nothing.
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 No.
It can't. Because you can't have, it doesn't work. They are infertile. They can try and breed as much as they want. But nothing, there will be no offspring. Okay.
There's a genetic.
Let's go the other way. Kilometers. We're coming dangerously close to talking about sex, and we don't want to do that in physics. Kilometers. Yeah, save it for biology. What kinds of objects do we measure on the kilometer scale? Can you be more specific? Because we've got roads that are reasonable to measure on the kilometer scale, but there are roads that are not reasonable to measure on the kilometer scale. Highway 1 goes across the entire country. You would not measure that in kilometers because now we're talking about tens of thousands of kilometers. That's a megameter. A megameter is 100,000 kilometers, a megameter is, this is 1,000 meters. This is 1 million meters. So a megameter is 1,000 kilometers. And 1,000 kilometers is it a country or is it even smaller than that? We'll pull up Google Maps and take a look. Okay, so what kind of objects would we measure on the kilometer scale?
Central Park.
What? Central Park. Here we go. Let's be specific objects. Central Park. For those of you who don't know what Central Park is the giant park in the middle of New York City. It is a large park, but is it a kilometer? We'll find out. What else? Sorry? The Loop. That is Mill Lake. Okay, so around Mill Lake. The walk around Mill Lake, it's totally reasonable to measure that in kilometers. It's like you said 2.5? Okay. So Central Park, question mark. That's park, not pork. But around Mill Lake, definitely that's on the kilometer scale. If you've never done that walk, that's your homework for next weekend. Go for a walk. Megameter. We're on the 1 million meters or 1,000 kilometers scale. Trans-Canada Highway. I actually have the length of that written down. Because this isn't the first time I've taught Physics 11. Someone said that before, and I actually have the measurement of that. Okay, so the Trans-Canada Highway is a reasonable guess. Yes, Abdu.
Megameter, right?
Yeah.
That's one moon. I think it's called Deimos.
What about the moon? Diameter, circumference, radius? What are we talking about?
Diameter.
Diameter of Deimos.
Yeah, Deimos.
That's an interesting moon to pick. Thor, you have another one?
Long distance flights.
What kind of long distance? Can you give me an example of a distance? Paris, from Paris to where? Vancouver to Paris. Van to Paris. You're suggesting is on the scale of megameters. Okay. I'll give you some answers here in a sec. Okay, let's go bigger. Gigameter. Gigameter. Careful. Think about this. A kilometer is 1,000 meters. A megameter is 1,000 kilometers. A gigameter would be 1,000 megameters or 1 million kilometers.
The galaxy.
4, 5, 6, 1 million kilometers. You're suggesting a galaxy. What about the star? Diameter, radius, orbit, what? Circumference.
Kind of
Circumference. I'm gonna get there. You're beating me to it. What kind of star? Okay, our sun. Cool. Circumference of sun. Darren.
Body,
Sorry?
the body of the sun.
The volume of the sun. We would have to measure that in cubic things, and we're not measuring cubic things. Cubic things gets... Volumes are actually surprisingly hard to picture mentally. Yeah, and we're not doing that. What else? Yeah, last one, Steven. Which planets?
Like, I don't know the exact, maybe like from a planet to a planet in our galaxy.
Pick 2 planets. Because the planet one's a difficult one too, because we're on circular orbits, right? Are you talking about when we're on the same side of the sun or when we're on opposite sides of the sun? Because those are going to be very different distances, right? So that's a hard one because what you've given is variable. Like different times of the year, those numbers are going to be very, very different. Last one, let's go to Andrew.
This isn't an answer. It's mainly a question, I guess, philosophy.
Pause. Hang on to it then. I want an answer. Not a question. Right now I want an answer. Abdu.
4 times the distance of Earth to the sun.
Did you look something up? That's very specific. You said 4 times?
Yeah, I remember.
Like back and forth twice?
Yeah. No, yeah.
Interesting.
It's from a video.
So, what is that? 4 AU. AU stands for astronomical unit. That is the distance from the Earth to the Sun. So what you're suggesting is 4 AU is a gigameter, or it's on the gigameter scale. Okay, cool. Let us take a look at some of these things. I have a few sites to show you. And I'm going to actually... No, don't look things up. Are you looking things up? Cheater. Okay. You betcha. I gotta mute this because the music's really annoying.
Can you ask this question?
No. Yes, Andrew, ask your question.
Technically speaking, nothing here says that we're supposed to answer or put down an answer that is like, how do I say it? These aren't supposed to be used. I can't say it.
Yeah, words are hard. It's okay.
Okay, here you go. The easiest way I can do it is technically speaking, I can put down the same exact answer for all of these and
No.
still be right.
No.
No, because nothing of it says that it has to be like a good estimate. So it can still be very uncomfortable and annoying to do, but it still be right.
Yes, if you're gonna look for technicalities, if you're gonna be that guy, then by all means go ahead. You can be that guy if you would like to be Andrew. I'm thinking a lot. Okay, so for those of you who are interested, do you want the music? The music's kind of annoying, but do you want the music to the site?
Yes.
Or do we want the musicless site?
You want the music? Here we go.
It's gonna be on.
It's like
pleasant, but trying to be epic.
I was gonna make the sound of the universe.
it's very quiet. It's much quieter than I expected it to be. Okay, here we go. So pick an object that you're familiar with from this. So this is called the scale of the universe 2, because the scale of the universe 1 shut down for reasons I don't know. So we're going to slide through this. We're going to go smaller first because that's what we did. So here we are on the scale of a meter. Some of the things that are on the meter scale, we talk about people. I mean, none of you necessarily know the dodo bird other than the fact that it's extinct. You might know of it. But this circle right here is a circle that is 1 meter in diameter. So you've got your average beach ball. You've got this gigantic flower. This is a worm. The giantest of all of the earthworms, this would be kind of scary to run into, is multiple meters long.
Where does it live?
Like in the ground.
No.
I don't know anything beyond that.
I thought it flew.
It does not fly. Okay, let's keep going. Okay, let's get smaller. We got your basketball. The largest hailstone ever was on the meter scale, which is horrifying. Imagine getting hit by that. Here's your teeny tiny hummingbird. You got your shrew. Let's keep going. Come on. Chicken.
Probably dragged it like the bar.
Let's keep going. I don't want to drag the bar. Don't tell me what to do.
Sorry.
This is sleet. This is a grain of rice.
Ooh, the green.
And this circle right here, just so if you're... This is the 10 to the negative 3. I'm going to drag the bar now. Nope, it's going the wrong way. I'm going the wrong way. Back. I'm dumb. Okay, so you said rice. Those of you who said rice, that's your grain of rice. This is your 10 to the negative 3. So any of these objects are totally reasonable. There's your ant there. We're actually at 10 to the negative 2 right now. So this, what you see on the screen right now, is the centimeter scale. Drops of sleet are like a centimeter. Grain of rice, your sunflower seed, you got your pencil lead here. Your ant is actually perfect, not your like mom's sister, but like the bug, is on the scale of the centimeter. Pick an object that you identify with here, and let's keep going. Yes. So here we are on the millimeter scale. The largest ever bacteria is that is terrifying. That should be terrifying. Is a millimeter long. That thing stretches basically across the circle. A grain of sand. Some of you said grains of things. So it's on the millimeter scale that says grains of things?
Yeah.
I wrote it down. There we go. You said grain of salt and grain of sand. There they are. Grain of salt and grain of sand. No, he's not on here. It's on centimeter scale.
Wait, what is that? What is that rainbow thing?
That rainbow thing is an LCD pixel. Where'd my mouse go? I don't know. I would like to know. Oh, there it is. There it is. Okay, so your LCD pixel is actually on the millimeter scale, not on the micrometer scale. There you go. So we got that one wrong. Dun, dun, dun. Screen pixel, there it is. There's an smite. There's an amoeba. Again, on the scale of millimeter though. So imagine you had one of those in your brain. That would be bad. They do that sometimes. Thickness of paper. So the thickness of paper as we scroll in here. This is like, yeah, human hair. Also kind of on the millimeter scale. Okay, so we've got a few things off here. The screen pixel is not on the micrometer scale. Hair. This is interesting. The smallest object visible to the naked eye. So you do not need a microscope to see this, and that's the human ant. Like,
Oh, what? Yeah.
once every 28 days, one of these leaves your body. Well, at least one of them leaves your body, ladies. 28 days, give or take. Depends how regular it is. It's called period. Gentlemen, for those of you who don't know what I'm talking about, never been married. Good, you don't know what I'm talking about.
I don't know that.
That is the size of human egg. Interesting. Keep going. You can see that. That would be weird and awkward. Silt is very small. Skin cell. Here we are. Cells. And so here we are. Oh yeah.
I think we were already at wavelengths. You thought it was.
Yes, and we are not yet at the micrometer. So this is infrared. Okay. Abdu, I think it was Abdu. You said
Colors.
wave of colored light. We are not there yet.
Just wait, so I guess
So those of you just to picture this for you, infrared light is heat.
they actually made contact lens let you see infrared lights.
That'd be really cool. So like when you look at thermal, if you ever had a chance to look at a thermal imaging camera, you've seen those on TV, maybe like the ghost hunter shows or like the, you're looking at the military shows. They're looking at things in thermal. This is the scale of the light that's being emitted. So light is actually, it's not small. It's a pretty big scale of wavelength of light. If you're feeling warm right now, this is what you're emitting. Light on that scale. I don't actually. What is thou and twip? I don't know. Here's your white blood cell. We're at 10 to the negative 5. The next, that little circle there is 10 to the negative 6. Oh look, there's the pathetic little Y chromosome. There's the X chromosome. And here we are on the micrometer scale. So chromosomes. Who said chromosomes for the micrometer scale? Well done.
Was me. I also said colors.
Oh, some of you said nanometer scale. Not. We're on the wrong one. We have to bump that up. Chromosomes are on the micrometer scale. And who said colored light?
Me.
There it is. Well done, Abdu. The largest virus.
Oh,
Also scary.
what is it though? What is that?
Don't know. That is called a bacteriophage. And the bacteriophages are the things that attack bacteria when they come into your body. We like bacteriophages, if I'm not mistaken. The smallest thing visible to an optical microscope. So these are the microscopes we have in the science lab. Your standard light that you look at with your eye kind of telescope is on the micrometer scale. Ultraviolet light's right there. It's very small. Much smaller than violet light. There is ultraviolet. This is the size of wavelength of light that will give you cancer, as opposed to looking purple. Fundamentally different. Let's keep going. Down to the nanometer scale. HIV's right there. Hepatitis B is right there. The transistor gate. This is the size of the gate that allows things to go in and out of your cells. For those of you who have taken biology or are going to take biology. That's what we're talking about there. Let's keep going. DNA. And that circle right there is the nanometer scale. Well, onward.
Adam, you're right.
Atoms. Whoever said atoms for the nanometer scale is absolutely correct. Whoever said proteins, you're close to proteins too, because proteins are sections of DNA. So, I mean, this circle is what? You could probably fit 20. That DNA chain might be 20 micrometers, 20 nanometers long. That's not unreasonable. Oh yeah, we're going all the way. Why would we go this far and not go all the way down? Glucose molecule, cesium atom, water molecule. So this is interesting for those of you taking chemistry. A single atom of cesium is substantially larger than a molecule of water. So there's periodic tables all around my class. Cesium is that bottom left-hand corner of the periodic table. That atom is substantially larger than water molecule. That is pretty intense. Let's keep going, because why the heck not? That's an angstrom. Don't ask me what it is, I don't remember. Helium atom, and we're going to keep going. Now we're at 10 to the negative 12. Nothing there, apparently. The femtometer. There we go. Uranium nucleus. An electron in the classical version, not actually. A chlorine nucleus. Helium. So now we're in the top right. Protons and neutrons. So proton is a hydrogen nucleus. We're on the femtometer scale. There were 10 to the negative 15, very small. So anything smaller. Oh, where is it? Come here, you mouse. Anything shorter than that length right there, we cannot actually prove. But we have objects down there, so let's keep going. That we think might be down there. So the weak force is the force that keeps protons and neutrons together in the atom. Anything further apart than this, and the weak force breaks down. Keep going. Quarks. So quarks are the building blocks of protons and neutrons. We're very, very small now. Oh, we got quarks down there. Charm. High energy neutrinos, very small. Yeah.
Top four.
Neutrinos were very small. It's interesting. High energy neutrinos are larger than low energy neutrinos. That should bother you a little bit. That would be like the higher energy version of you being substantially larger than the I'm tired at the end of the day. It would mean like you got shrunken. As you got more tired, you got smaller. That's weird. Should make you uncomfortable. Here we go! Smaller still. Oh, there's things. We're just not there yet.
What?
They're too small for you to see. They're going to buy them.
We also haven't confirmed this. Here we go. Oh, no! Stupid machine.
It's okay. It's all good. It's all good.
Oh, don't tell me what's good at it. I will tell you.
It's all good.
There we go. Back down to where we were.
I feel like I'm going to like
Here we go.
like, oh,
Blank length.
Oh, like,
what is a string?
So, like in string theory,
Oh.
this will be the size of the strings.
Quantum.
Yeah, quantum foam. What's that? Great question. Nobody knows. Okay, so now here we are at the bottom. Let's go back to the middle.
Everyone's just guessing at this point.
Back to the meter scale. Interestingly enough, the average size of all the things in the universe is a meter. Here we go. Let's go bigger. because we're running out of time. So let's get to the kilometer scale. There it is. The length of the Hoover Dam is about a kilometer. The Eiffel Tower is like a third of a kilometer. This is that half dome.
I saw someone find that so much.
The Angel Falls. So this is the waterfalls from the TV show Up. Here we are on the kilometer scale. Burj Khalifa. This is I think this is still technically the tallest building on the planet. Is on the kilometer scale. The Boeing factory in Everett is on the kilometer scale. Uluru. This is the fancy big rock in the middle of the Australian desert. I wish I would have been there.
I hit my head on that.
You hit your head on it. Okay, bigger. Demos.
I think I read it.
Whoever said Demos. Demos is not on the megameter scale. Demos is substantially smaller than that. Neutron stars, Rhode Island. We're not even on the megameter scale yet. That is the megameter scale. That circle right there.
Italy country.
Italy. Italy's on the megameter scale. For those of you who said the Trans-Canada Highway is 7 megameters. So also on the megameter scale. Totally valid.
7 times Italy's?
7 times the, well, a little bit less than that because Italy's slightly bigger than a megameter. Let's go faster. Pluto. Oh, that's a very small planet. The Great Barrier Reef.
United States of America.
Yeah, the US, Asia, Venus, Earth. We are on the 10 to the 7. Uranus, Saturn. Here we go. That circle there. Now we are on 10 to the 9.
Oh no.
Megameter.
The sun.
Our sun is right there. Whoever said the sun, and it's not the circumference, it would be the diameter. The diameter of the sun is on the gigameter scale. And I know the bell's going to go here in a sec, but let's go bigger until the bell goes. Because why not? Things get ridiculous.
Oh, you tried.
All the people who have ever lived, if you stack them up,
Yeah, you did it.
you get to theirs. That's pretty cool.
We're naming these planets.
I don't know, these are stars, these are not planets. Here, oh, who said, oh, pause. Who said distance to Earth the Sun? You're wrong. 4 times this is like on the 10 to the 12 scale. This would be bigger than a gigameter.
That's super
There we
fun.
go. Bigger, bigger, bigger. There's the Kuiper Belt. This is like the outer edge of our solar system. Sorry? Why not? This is a light day. The distance light travels in a day is the distance from, well, is across our solar system at its widest point, which is pretty
slow.
to give you a perspective.
Pretty slow.
The distance from Sedna to Earth. Sedna is, whatever. Stinger Nebula is pretty big. Another nebula. Light year. Here we go. Let's keep going. A parsec.
Bubble?
We are on. There's that circle is 10 to the 18. Sorry, 10 to the 18. Like, so now we're on this. As soon as you hit space, the scale just gets incomprehensibly large.
Black hole.
Neil?
Wait for me. Black hole.
Fucking sombrero?
So the Milky Way is on the 10 to the 21 scale. So those anyone who just said black holes are not the size of galaxies. They are objects at the center of galaxies.
They're bigger. There's
No,
one
they are substantially smaller.
There's one that's much, much bigger.
Yes, but that's vastly the exception.
Yeah.
Yeah, and here we go.
Local.
This is not even comprehensible now.
Black
The local group is our section of the universe. And then let's go all the way to the observable universe. Here we are. There is the observable universe. We are on the 10 to the 26 scale at this point.
Wait,
So
you
the
got
size, because we have objects on the big size and on the small size, scientific notation is wildly useful. I thought this was a fun little exercise just to blow your mind a little bit. Tomorrow, you have no homework. Tomorrow we're going to get into algebra and rearranging things. So if you've been scared when math comes tomorrow, when the bell goes, you may also go have a super duper day. We'll
Wait,
see.
how big is the great attraction?
The great attractor. I don't know. The last thing is the observable. See you guys later. Yeah, it's getting a little ridiculous.
Sombrero Galaxy.
It looks like a sombrero someone thought, and therefore it is. Okay.